Everyone, thank you for coming. I see some new faces compared to last year. I see some familiar faces also. I'm Sylvan Brocard. I'm a SDK architect at UPMEM. So, as Jan mentioned, I'm going to talk a bit about the physical architecture of the PIM DIMs at a high level, and then their programming model, and then about the new stuff happening in the SDK and hardware-wise. Okay. So first about the high-level hardware architecture. So the PIM are, they are DIMs. They look like regular DIMs. We put them in a RAM slot in a server. They are divided as 8 chips per rank. So a DIM has 2 ranks each side of the DIM. And so in each of those chips, you have 8 64 megabyte memory banks that you're going to use to store the data that you use in your computation on the DPUs. So those banks are accessed directly by the host CPU, as a regular memory. And then attached to each memory bank, there is a DPU, which is of an embedded processor that can access this memory bank very fast and very efficiently. And there is also a control interface that lets you control the DPUs. By controlling, I mean, starting the DPUs, stopping the DPUs, checking if they are in fault, that sort of thing. And this control interface, it's used by writing into memory. So all the host CPU is doing is writing into memory. I mean, basically half the address range is used to communicate with the memory banks, and the other half is used to write instructions that are going to be read and executed by the DPUs. So let's look a bit about what a DPU looks like. Functionally, this is a functional schematic. It's not a topological one. Of course, in reality, on the real die, most of the space is taken by the 64 megabytes of memory, and then the DPU is like a small square in the middle of that. So about its architecture. So I'm going to talk a bit later, about the pipeline, but what it means is that there's an instruction pipeline. There are multiple threads running on the DPUs. Each of those threads has its own set of registers, its own PC, but they are all executing the same program that's stored in the instruction memory. The instruction memory itself can only store 4,000 instructions. It doesn't seem like a lot, but it turns out we can do quite a few applications with just that. The DPU also has access to a scratchpad memory of 64 kilobytes that we call the working RAM. This is what you use when you're doing stores and loads. This is your directly accessible memory. And when you want to read or write from the main RAM, you're doing it through a DMA engine. So one important thing to note, of course, is that there is a MUX here, right? And this MUX implies exclusive ownership of the MRAM by either the DPU or the host processor. And the reason for that is there's no, this is because of the DDR protocol, right? It would be too hard to have the DMA from the DPU and the HCPU from the host, somehow, accessing the memory banks at the same time. So only one can read or write into it at the same time. So about this pipeline, right? So the way it works is each instruction that you execute is divided into 11 steps. But instead of having every thread going through 11 steps and then the next one and then the next one, the pipeline is always fully populated. And because it's 11 steps deep, that means you have effectively at most 11 threads running concurrently. And okay, I forgot to change that. I said you can have 24-hour threads at the same time running. In the new version of the hardware, we limited that to 16. Mostly because nobody was using 24. It's still worth it to use a bit more than 11 hardware threads. 16 is a nice number, obviously. It's a power of 2. And also because not all the threads are always able to run. Sometimes they're waiting for synchronization. Sometimes they're waiting for DMA access. And in that case, it's nice to have a few more threads that's going to sort of smooth over this slowdown due to waiting on stuff. Yeah, there are 32 registers per thread, 24 regular ones and 8 constant ones. And okay, maybe I should mention, right, a bit of the reason for this whole thing, right, this whole programming model. I mean, you have to remember what we're doing. We are carving a processor into memory technology, right? So it's not like an x86. We don't have 12 layers of wafers to do some complex piping and everything. So the processor has to be simple. We can't have, out-of-order execution and automatic pipelining that you have on x86. That's why we have to sort of expose parallelism to the developer. So the typical workflow when you're working on a DPU is to first do the initialization. So what we mean by initialization is allocating the DPUs, starting a bunch of threads on the host that are going to be responsible for polling the DPUs, ensuring that everything is coherent in memory and so on, and also loading the program. And then the typical execution loop is, well, first you push some data onto the DPUs, then you start running the program, you wait for the end of its execution, and then from the host you read the results back from the DPUs. Another last thing, and maybe one of the most important things to note about the hardware architecture that has consequences on the way we program. So when you're using regular DIMM, right, regular RAM on an x86, well, any sort of CPU really, what's happening when you're writing a double word into memory is that it's split into bytes, and each of those bytes are sent to a different bank, something like that. Right? And because this is what's going to guarantee you, the maximum throughput, the minimum latency, and of course, when you're programming on a CPU, it doesn't matter for you, it's transparent because you're scattering this data to all those banks, and then when you're reading, you're gathering from all those banks, so it doesn't seem like anything is happening. Now, when you're programming on DPU, it's more of a problem, right? Because probably, on your host, on your application, you have a buffer that exists for a reason, that has like that is logically contiguous. But when you're writing it into the DPU, if you're scattering like that, randomly, from the point of view of one DPU, you're reading random bytes that don't really make sense. So you would want your continuous host buffer to also be contiguous on the DPU. And that's why the SDK does something, right? When you're writing into the MRAM, it's actually grabbing 8 double words, and it's doing a transposition so that contiguous buffer on the host ends up being contiguous on the DPU. The consequence of that is that for this to be efficient, you want to be doing that for multiple DPUs at once. Otherwise, you're going to be using only 1/8 of your bandwidth, and that's not going to be very good. So that's why there's this API in the SDK where you sort of specify all the data you want to send for all your DPUs beforehand, and then you launch the transfer, and the transfer happens for all DPU at once, and that's why it's going at the maximum throughput efficiency. So let's talk about programming. Sorry, about the programming model of the PIM. Right. So let's talk a bit about what the SDK looks like. So you're going to be writing driving code every time from that's going to run on an x86. For now, we only support x86 as a host platform. We provide some host libraries to do all the CPU synchronization and orchestration and so forth, and loading DPU programs, booting the DPUs, etc. On the side of writing the embedded DPU program, it's written in C. It's not, there's not the whole entire C standard library. There's nothing for input outputs. Obviously, you don't have like the regular malloc. There are some lightweight allocators. You don't have the math library, and so on. Usually, when we do an application, we write a single program that we execute on all DPUs, but it's not. You don't have to. You can have different programs, different DPUs doing different jobs. The compilation is done, with a fork of Clang that we provide that's enabled for DPUs. In the library, there are some primitive functions for thread synchronization, for reading into the MRAM, doing some performance counting, and so forth. Oh, yeah, by the way, I forgot to mention on the CPU side, the host application can be coded in C, but there are also bindings for C++, Java, and Python. When it comes to profiling and debugging tools, so we have a version of LLDB that works for the DPU. That means you can attach to a running DPU program, and then you can step through it. You can observe the memory state, everything you can do in LLDB. You've got DPU trace, which is a tool for tracing your execution, getting some statistics of how much time you spent in each function, and so on. On the host side, we've got DPU profiling, which is quite a useful tool that's going to output an execution chart that you can read in Chrome, and that's very useful to see what's going on from the point of view of the host. Are you spending a lot of time waiting, doing nothing on different threads, and so on? So all the servers we provide run on Linux. You need a driver for the DPUs, and you also need a BIOS patch for the server. This is quite a heavy dependency that we're trying to phase out. But for now it's still there. I mean, basically, you have to tell your server that you've got this weird exotic memory. When you boot, don't try to test it, because it doesn't work like regular memory. And so without this patch, you wouldn't be able to boot the system at all. So about the instruction set for the DPU. So it's a proprietary instruction set. It's RISC-based. It's triadic. It has some inspiration from RISC-V, but it's quite a bit different. It has some limitations, right? First off, there is no FPU on the DPUs. You can write floating point arithmetic in your program, and it's going to execute, but all this arithmetic is emulated, so it's very slow. The example here being that it takes about 200 cycles to do a 32 by 32 float multiplication. So for anything that's performance sensitive, you should consider quantizing your data before doing any operation on it on the DPUs. So another property that there are no vector instruction, except for one, which is CMP-before, which lets you compare 4 bits integer one by one, but it's a bit of a special case. When it comes to other arithmetics, integer arithmetics, there is an 8x8 multiplication that can be done in one step. And when you're doing a 32 bits multiplication, it does something a bit different. It does a mul-step based algorithm. It does the same sort of multiplication you learn in school, digit by digit. And so in the worst case, it's going to take 32 operations to do a multiplication. But if one of your operands is small, it's going to be a lot faster. It's going to terminate early. And for additions, that's fine. You have 32 bits addition. So this was more, limitations. Now I want to talk a bit more about like an advantage of it. Is that almost, I want to say almost all the arithmetic operations and other operations have some sort of conditional jump that you can use with it. This makes branching very efficient on DPUs, especially because not only you're saving one instruction, but like since there's no branch prediction, automatic pipelining, or anything like that, branching is free. I mean, it's an instruction like any other. So if you're used to x86 HPC code where you're trying to never branch, this is not a concern on the DPUs, and that's what makes it good for applications like decision trees, where you're always branching. That's it. And yeah, another thing to mention is that it's worth it really to look at your code, especially at the important hot loops. Look at what's going on. Sometimes there can be some missed optimization. There can be some small changes in your code that can really make a big difference. So it's worth looking at it. And you can dump your program as an assembly file, of course, but we also have a website that's dpu.dev that's just like Godbolt, but specifically for DPU programs. So you can just put your C code in there. It's going to show you the assembly. So yeah, speaking of optimizations via conditional jumps, so here's an example. Is the 16-bit multiplication. So yeah, which is just a small program. You take two 16-bit integers, you multiply them, you return a 32. This is, the compiled code that performs that. So what's important is this first multiplication, right? It's doing multiplication of the least significant bytes of the two operands. But then you see, okay, there's a condition. Condition small is a condition that's true if both operands are, fit in 8 bits. And we say, okay, I'm multiplying 16-bit integers, but if both my operands fit in 16 bits, then I jump, to the end, and I'm done. I don't have to do anything else. So, this is quite a powerful feature of the SDK because it's of the ISA. Because that way, sometimes you might need a 16-bit integer, but you know that most of your data is going to fit in 8 bits. Well, you're not going to lose any performance because whenever you're doing 8-bit multiplications, you're still going to do just one instruction, and then it's going to be over. Another useful aspect of those conditional jumps is, well, you can write reverse loops. This is, I don't know, some of you have experience in embedded. This is like a classic trick, right? It's better to loop from a number to 0 because then you can test for the 0 condition at the end. It's cheaper than testing for a comparison between I and size, and that way you're saving yourself a bit of cycles, and that way, yeah, you've got this operation that decrements the loop counter and tests for 0 at the same time. So you're saving one instruction every loop. That's pretty nice. Yeah, I want to give another example of why it's worth looking at your compiled code. It's something that happened to me that left me quite baffled when I saw it the first time. And I want to do a quick pop quiz, if you're fine with it. Can anybody tell me, if actually, in this example, what's happening according to the C standard to those two operands when you do this operation? Does anybody know? When you have two 16-bit integers, and you multiply them together, what does the C standard tell us happens to those integers? Really? They get promoted, right? They get promoted to 32-bit integers before being multiplied. That's a limitation of the C language, right? That means there is no portable way to say, I want to do a 16-bit multiplication. You kind of have to rely on the compiler to be nice and say, oh, I noticed that you only need a 16-bit multiplication, so I'm going to give you that. Like any optimization, it can be missed. And that's what I want to talk about. So this is more or less something I was coding at some point. I was trying to write a Euclidean distance code, well, squared Euclidean distance, I guess. So you're going over some tables, you're computing a difference of two integers, and you square the difference and you add it into an accumulator. And you would think, okay, my operands are int 8, my bad, that's my input. I'm computing a difference, so it should fit into 16. But then, yeah, the difference is going to be, less than 16 bits. So when I'm doing this squaring, I should be doing a 16-bit multiplication. And if we look at the code, we see that it's not happening. Actually, we're calling mul SE3, which is the 32-bit integer, signed integer multiplication. So that's very unfortunate. What happens here is that, in my understanding, is that so the compiler sees this diff, it goes, oh, well, actually you're just using it here, so it's not a real variable, you're not going to keep it, so I'm going to optimize it away, and then it does, it rewrites this line into this line, and then it follows the integer promotion rules, and you end up doing 32-bit multiplications. So there's a workaround for that. Just make it volatile, right? Force the compiler to actually first do the difference, store that into a 16-bit, and then actually multiplying two 16-bit integers together, and you see that, yeah, you get the 16-bit multiplication. You also get a lot fewer, like, I don't know why, there's a lot of useless moves here, but disappear. That's nice. So let me show you some basic example of how you program for the SDK. All right, so this is like a really dummy, really basic example, just to look at what the code for a DPU looks like. Typically, yeah, you're going to include this header that comes from the UPMEM library for DPU that lets you write and read to the MRAM from the DPU. It provides you with this little specifier that you can add to variables to say, hey, they should be stored in MRAM. There's also this one, the DMA align. So here we are doing the local variables that are going to be stored in WRAM, but I'm going to want to read and write from the MRAM, from those variables into those ones. And for that to happen, they have to be correctly aligned. And this is what this specifier tells you, okay, this variable can be used to be copied or to copy from the MRAM. And so, yeah, you can use MRAM read and MRAM write to write to and from the MRAM. And that's going to cause some DMA transfers. From the host perspective, I also want to show the basic example that goes with the previous DPU code I just showed you. Okay, so first thing to notice, there's a lot of DPU asserts. Macro, here. This is what we use to do error handling in the SDK. Almost all SDK functions return an error code, and the DPU assert macro will just check it. If it's not 0, it's going to print the correct error message and crash your program. So anyway, about this example, typically what you're going to do first is allocate some DPUs to your program. You're going to load a DPU binary by giving it its name like as a string. And then, okay, in this loop, we are going to prepare a transfer where we're going to write from our data on the host into the input array on the DPU. And we are giving it the name of the variable as a string. How does the DPU do that? Well, when you load a program into the DPUs, the SDK will parse the ELF file of the program, will parse the binary, and will store the address of all the variables that it's allowed to communicate with. Then after we have prepared, after we have transferred the data, we're going to launch the execution of the DPU. And in this case, we are launching it in synchronous mode. So synchronous mode means that it's blocking. You're going to start the DPU and then wait until the execution is over until resuming. There's also, of course, an asynchronous mode, which is more complex, where you can start execution of the DPU, do something else on the host, or do something different on different DPU ranks, and so forth. There are examples, of all that on the online documentation. Okay, and then at the end, you gather your results on the host side. So now I want to talk about new stuff. So first one being the scatter-gather transfers. It's not really new. It's been in the SDK for a while now. I don't remember, last year maybe. But we didn't talk about it last year here, so I want to mention it. It's been a pretty important addition to the SDK. So basically, the issue is that with the regular transfer API that we provide, you can only transfer blocks to GPUs that all have the same size. And it's quite limiting. There are many cases where you want to get some logically contiguous blocks from the different DPUs and gather them in memory on your host, but they may be different size. Typically, if you've been using the DPUs to do some sorting or some hashing, you can't predict exactly what the size of each block is going to be. So that's why you need an API like that to do this sort of more flexible transfers. It can be used in both directions. Like this is a gather, and you can also do a scatter of sending memory of different size to different DPUs. It uses a functional API. What I mean by that is that we don't make you fill a table of pointers or something like that. The SDK does it in the background for you. Instead, what you provide is a function where you tell, okay, for DPU N and block M, I want to send data that starts at this pointer and that has this length. And it returns a bool. So bool says, okay, for this DPU index and block index, true, I have something to send. False, I don't have anything to send. That way, the SDK will use that function to sort of fill a transfer table and do all the behind the scene synchronization and all that. It's been used with quite a bit of success for some internal applications, and I'm sure we've received a lot of comments from users that they find this API quite useful. So another new thing, it's not really a new feature, it's more of a bug fix, but I think it was important to mention. Basically, when was it? It was last year. We started receiving a lot of messages from users that their benchmarks were slowing down, like by a lot. They had lost 100% performance. I mean, twice slower, thrice slower. And we didn't see any of that. That's mostly because on our cloud, we are still using Debian 10, whereas those users were using Ubuntu 20 or Ubuntu 22. And what happened last summer is that Intel deployed security mitigation to the microcode of their CPUs. And this caused gather instructions to really slow down. I mean, now they announced that it takes 30 cycles to do a gather instruction. And that's what was causing the issue. So actually, we got the solution from Manuel Penchuk from Frankfurt University. He contacted us. He did some experiment. He did some modifications to the SDK backend, and he contacted us with a solution because we were using a gather instruction in the SDK when we do the whole memory transfer thing, where we do the transposition and all that. It was a very critical instruction. So I mean, you did two things. First, there's a fix, right? So instead of doing a gather operation that takes 30 cycles, you do a regular load operation. AVX load, or 1 cycle, and then AVX permute, 1 cycle also. So it's a lot faster. You can check out his repo. He has done some also much more sophisticated improvements to the bandwidth of the transfer of the GPU. It's not, we didn't integrate it into the SDK yet, but yeah, he's done some very clever things. Mostly, instead of doing one permutation of 8 by 8 bytes, he's taking a much bigger matrix, and then he's doing a sort of recursive permutation, and that way you can save a few cycles of compute, and you get interesting performance improvements. Yeah, and I guess it's a recommendation for everyone. Don't use gather instructions anymore. It's not worth it. Another new feature that's coming into this release that we're going to do hopefully this week, at least very soon, and that is the WRAM parallel access. So this is like the regular asynchronous mode that we had already. So the asynchronous mode, all it means is that you can sort of schedule jobs whenever you want, and then they get executed for every DPU rank in the same order, but with different timings. Sometimes you want something a little bit different, right? What you would really like to do is, during the DPU execution, be able to do something with the DPUs from the host. You want to maybe to not have to stop the DPU execution, to get some result, to send some flags, atomic flags to the DPU. I mean, there's all sorts of synchronization that you might want to do with that. And now you can, but I have to mention it, this is a big feature of the V1B hardware. You can't use the parallel mode on V1A because of hardware constraints that I don't really understand. Now, okay, the thing is, you can use, you can use some raw accesses, in parallel mode, that's fine. But actually programming with it, it's quite hard, there are a lot of things to arbitrate. You have to make sure that everything is synchronized, everything happens in the right order, and so on and so forth. So that's why in tandem with the WRAM parallel access, we provide sort of a FIFO API, which is not unlike channels in Go or Rust, where you're going to, from the host, push some data into an input FIFO, read it, use it from the DPU, push the result back into an output FIFO, and it's it's a way to simplify the job of writing applications that do WRAM parallel access. This is roughly what it looks like. On the DPU side, let's say, okay, you're going to create a host variable. A host means this can be read and written to by the host. That's going to be sort of a flag to say, okay, stop the execution. That's going to come from the host. You need to create a barrier yourself, and you have some macros to initialize input FIFOs and output FIFOs. And the big function that you're supposed to use in this API is this: process inputs all tasklets, to which you're going to give an input FIFO, an output FIFO. A function values some compute that's going to be executed in parallel on all tasklets to process data from the input FIFO. A function values some radius that's going to be executed just on tasklet 0 to get the result and put them back into the output FIFO. And then the barrier and synchronization stuff. On the host side, okay, first thing first, for readability, I removed all the DPU assert. Don't do that, it's just for the slide. Please use DPU assert. And so typically the way you're going to use that, you're going to launch the DPUs in asynchronous mode, and while the DPUs are running, you're going to use DPU FIFO, push xfer to write to the DPUs, also push xfer to read from the DPUs WRAM while they are running. You can also do some callbacks that are going to run on the host, but there's going to be one execution for every DPU. And then you can sort of use here this active variable as a flag, and you can send it to the DPU through the with this flag, DPU XR parallel. So during the executions, the DPUs are going to see this being changed to 0, and and when it is 0, they're going to stop the execution of this function, and they're going to return. That way, you can dynamically control the execution of your DPUs. Another new thing, which is not going to come right now, not in this release, unfortunately, but in the next release, function overlays. That's something that's been asked a few times. That came, for example, from when we did an application on databases, right? We did the join application. It's nice. It works really well in terms of performance, but it's already using most of the instruction RAM on the DPUs. And so having a join is nice, but if you want a full DBMS, you want a lot more functions than just a join. And problem then, it will not fit into 4K of instruction memory. And so what we're currently developing is what we're currently testing is this concept, but something that exists already in some embedded systems mostly, where you're going to have a program in memory that's going to be always loaded. By program I mean the function main, maybe some other, and then you're going to have a number of functions in an overlay memory, and you're going to have a bunch of functions stored into MRAM. And then you can dynamically, during your DPU execution, fetch some functions from one of those overlays and put it into the overlay area, and switch it with the existing one. And that way you can have much larger binaries. And the way this is programmed is something like that. Okay, you have your functions, you decorate them with a property like that, telling them, okay, you're in this function group. And then there is this macro that you can use. So obviously this macro should be used when you're not in a function group. Right? It should be used when you're in the program that's static, that's not moving. And it's going to tell all your tasklets, all your threads, to sync, to reach this barrier. And when they are all there, when they're all synchronized, then you can safely switch the overlay to another one. So it might seem a bit restrictive as a programming model, and it is subject to change. But right now, our main priority is to have something that that doesn't introduce programs that are really hard to debug, because obviously this whole manipulating instruction memory, it's very touchy, it's very sensitive. Actually, most of our testing effort and debugging effort so far has been on making sure that this all works with LLDB. Because obviously, you want to debug something like that, it's not trivial. But to help for debugging, we also have some extra macros like that. You can test which function group is loaded. You can make sure that your preconditions are actually what you think they are. And hopefully you will enjoy this new feature. That is all for me. Do you have any questions?